Welcome to Introduction to Limits. Before we can talk about limits, we're going to talk about sequences. And a sequence is just a set of numbers in a particular order. And we're interested to know whether or not the sequence grows without bound, it oscillates, or it appears to approach a specific number. So in this first example, 1, 2, 3, 4, and the ... implies that we continue in the same manner, growing by 1 each time. So the next would be 5, 6, 7, 8, etc. So we would say that this grows without bound. The next example is 1, 1, 2, 3, 5, 8, 13. And you may recognize this sequence as the Fibonacci sequence. We add 1 and 1 in order to get the third term in the sequence, 2. And then we add 1 plus 2 to get the fourth term in the sequence, 3. Then add 2 and 3 to get 5. 3 and 5 to get 8. 5 and 8 to get 13. The next term in the sequence would be 8 plus 13, or 21. And this continues on. So this one also grows without bound. The next sequence, you'll see, bounces back and forth between +1, 0, -1, 0, 1, 0, -1, 0. So it just keeps sort of bouncing back and forth between -1 and 1 and going through 0. So you may or may not know what the word oscillate means, but if you've ever seen what's called an oscillating fan, it's a fan that moves back and forth. It oscillates. So this one oscillates. The next sequence is 0.1 or 1/10, 0.01 or 1/100th, 0.001 or 1/1000th, and so on and so forth. So each of these numbers is getting smaller and smaller in terms of its size, its value, its absolute value. And in fact, if we continued on like this, we'd be getting closer and closer each time. If we tried to plot these on a number line, we would get closer and closer. We would be approaching 0. The next sequence is 1, 1.5, 1.9, 1.95, 1.99, 1.999, 1.9999. And in this case, the numbers aren't necessarily getting smaller, but they're not growing without bound like in the first two examples. We started at 1, and we seem to be slowly increasing our fractional part of our number and getting the fractional part of our number closer and closer to 1. So overall, the sequence is approaching 2. Each number in the sequence gets closer to the number 2. Again, if we plot those on a number line, we can see that progression towards 2. So when a sequence has that characteristic of approaching a specific number, we say that sequence has a limit. And when discussing limits, we may never reach the limiting number. If we think back to the example where we approached 0 and we approached 2, each number in that sequence was getting closer and closer to 0 or 2, but if we kept following that pattern, we never actually write down the number 0. We never actually write down the number 2 in that sequence. Next, the limit must be unique. Right? So one might argue, well, we could just pick out, in the one that oscillates, just pick out all the zeros, and then we've got a sequence that goes to 0. But I could also argue, well, we could pick out the 1s, and the sequence would be approaching 1. So in that case, it has to be unique. We can't be going to two different places. And when it does not have a specific number, we say it does not have a limit. And if the sequence grows without bound, like we did in the first two, then we're going to say that the limit is either infinite or negative infinity, so positive infinity or negative infinity. Depends on the sequence of numbers, whether their sequence of numbers is positive or the sequence of numbers is negative. So let's apply this idea of using the term, does this function have a limit, or what is the limit? to these examples that we just did. So if we recall, the first example grew without bound. So we weren't approaching a specific number, but we were growing without bound in the positive direction. The numbers were getting larger and larger in the positive direction. So we would say the limit is positive infinity. Similarly, the next one, the Fibonacci sequence, each number is getting larger and larger and larger. So the limit here is also positive infinity. The next sequence, this was the one that oscillated. We didn't have a single sort of number that we were approaching. We were bouncing around. So we say does not have a limit. The next sequence was the one that was approaching 0. So we would say in this sequence, the limit is 0. And in the very last one, we were approaching 2, so we would say the limit is 2. So now, in order to use this concept in calculus, we're going to start by asking the question, well, what happens if I create a sequence, for example, the sequence 1.9, 1.99, 1.999. We start creating a sequence, okay? And that sequence is approaching 2, right? Each step along the way in that sequence, we're getting closer and closer to the number 2. Now, what happens if I plug that number into 1 over x, that sequence of numbers into 1 over x? I want to know what happens to this sequence of outputs. So we'll get a new sequence. So we're going to take a sequence of inputs, put them into the function 1 over x, and I want to know the sequence of outputs that we get. Does that then have a limit? That's the question I want to answer. So you're going to need to break out your calculators real quick, and I'll give you a moment. You should hit pause at this point, and I will give you a moment to figure out what all these outputs are. And then when you come back, you can compare your answers to mine. Welcome back. So hopefully you took the time and actually did these calculations. And what I'd like to focus on now is this sequence of numbers. Okay, and if we write them out, the sequence looks like it's approaching. Notice what's going on here. We're getting more and more zeros between the 5 and the 2, right, each along the way. So the first one was 0.526316. Next one was 0.502512. Next one was 0.500250. Next one was 0.500025. And then we've got 0.5123 zeros and then a 3. So we're basically starting to pile up more and more zeros after the 5. So in general, we would say we'd notice this pattern, and if we continued on in this way, we would say that the sequence of those numbers approaches 0.5 or 1/2. Okay, so if we look at that sequence of numbers, they're getting closer. Each time we put in a 1 with more and more 9s, that number is getting closer and closer to 0.5. So mathematicians like to take a long question like, what number is 1 over x approaching if the inputs of x approach 2? So mathematically, we write this as the limit of 1 over x, so I'm telling you my input function is 1 over x, as x approaches 2 from the left. Now, why from the left? And I want to point out right here, this little minus sign that's used as an exponent. Now, it's not an exponent. It's giving us some information. That's this idea of from the left, okay? So what I mean, I'm approaching 2 from the left. If we think about a number line, and we think about where number 2 is on the number line, 3 is on the right, 1 is on the left. And remember, my sequence of inputs started at, now I know this isn't quite to scale, but I'm going to run out of room quickly if I don't do it this way. 1.9, and then 1.99, and then 1.999, and 1.999. So notice I started on the left of 2 and I snuck up on it, or I approached from the left of 2, right? So that's why that little minus sign is there. It's telling me, how did I create my sequence of inputs? Well, I started to the left of 2 and I created my sequence so that I got closer and closer. And students might ask, well, do I have to use 1.9, 1.99? No, it's just an easy sequence. You can choose any sequence you want as long as it starts on the left of 2 and then slowly approaches 2 or quickly approaches 2, however you want to think about it. But the idea is to create the sequence so that you have enough numbers in the sequence so that if you create the table like we did, that you'll be able to see the outputs and clearly see the trend there, the sequence, what number that sequence is approaching. And then in this case, the sequence was approaching 1/2, the sequence of outputs, right? So the 1/2 was from the sequence of outputs have a limit of 1/2 if I use the function 1 over x, right? And I approach from the left. So since there is a from the left, one might guess that there is also a limit from the right, and we would want to take a look at that. And that is true. That's what we're going to do next. And we're really interested in not only this limit from the left and then from the right, but do they equal each other? Do we end up at the same limit? Okay, so we're going to do that. We're going to take a look as x gets closer and closer to 2 from the right. So I'm going to draw a quick number line here. 1, 3, and so we notice 3 is to the right now. So I want to pick a number that's between 2 and 3, and we start at 2.1. Again, you don't have to start at 2.1. We just need to make a sequence, create a sequence that starts on the right of 2 on the number line and moves toward 2. So, 2.1, 2.01, 2.001, 2.0001, etc. Okay? So again, at this point you should hit pause, do the calculation in your calculator, fill in the table, and see what we get. I will wait for you. Welcome back. So hopefully you did your calculations and you filled out your table. And again, the idea is we build a sequence of inputs that approaches 2. And again, don't have to use this one, but this one is easy because you're just hitting the 0 button a lot and the 1. And we want to put that into 1 over x and see what the sequence of outputs look like. So I want to focus on just this sequence of outputs right here. Okay? And I want to take a look. Are they getting closer and closer to a particular number? Do they have a limit? And as we move down the list here, right, we move down the sequence, we start to see we add more 9s each time, right? So 0.499. The next one would be 0.499999, right? More and more 9s. So again, what is the limit here? The limit of outputs is approaching 0.5 or 1/2. So as x gets closer and closer to 2, from the right of 2, 1 over x gets closer and closer to 0.5. So we'll take a look at what this looks like mathematically. So mathematically, we write this as the limit as x approaches 2 from the right of 1 over x equals 1/2. Again, we want to point out this little plus sign is the one that indicates that's how I've looked at this limit, as the set of inputs approaches 2 from the right. And so when I do that, when I build a sequence that approaches 2 from the right, that has a limit of 2 as I come in toward 2 from the right, and I plug those into 1 over x, this is my output, right? Limit of output sequence is 1/2. So now we're going to put these two together because we notice that as we approached from the left, the limit was 1/2, the limit of the outputs. And as we approach from the right, the limit of the outputs is 1/2. So when that happens, when the left-hand limit and the right-hand limit are the same, we state that the limit of 1 over x as x approaches 2 is 1/2. Now implied, as x approaches 2, implied is from the left and from the right is 1/2. And when they are the same from the right and from the left, we can say the limit is this. Now notice one difference here that is not in this problem, that was in the others. Notice there's no plus or minus there where they were in the previous ones. So notice the absence of a plus or minus actually means you have to do both. If you have a plus or minus, you only have to do one. So this tells me, this piece of information, the fact that there is no plus or minus means must do limit as x approaches 2 from the left of 1 over x and the limit as x approaches 2 from the right of 1 over x. And if they are the same, then I can say that the answer to the limit is 1/2. If we end up with two different limits there from the left and from the right, which is possible with some functions, then we say that the limit does not exist, right? So if they are not the same, then we say the limit does not exist. So that's sort of a quick explanation of the left-hand limit, the right-hand limit, and the limit. The next video I want you to watch is the one where we're actually going to do some examples of this using our graphing calculator.